Piecewise defined functions have at least two defined rules that are used for different parts of their domain. Absolute value, irrational, radical step functions, and others can be used in a piecewise. Different rules may be applied to separate parts of the domain. Rules are written using large brackets, so as you can see right here, this is the large brackets that they're talking about. The word if is sometimes used, and to evaluate, you need to determine which part of the domain that the function is in and apply the rule to it. So you need to keep track of the domains, which are located right here, and that's going to specify which of the two, in this case it's two equations, we're going to apply that to. You can have more than two equations, it's multiple equations, but over the restrictions of the domain is what is going to be graphed, and then we look at the graph in terms of the entire graph, even though it's done in parts. So down below here we're asked what the domain and range is, and as you can see, this part of the graph for x plus 2 is going off to negative infinity. And as we continue from the point 1 of the domain, it stops right here at 4. As far as the range is concerned, we're going down towards negative infinity this way because of this line to the left. And as we go up the y-axis, it stops at a positive 3. So going back to the domain, we're at negative infinity, comma, 4. It includes 4 because this solid dot tells me so. Infinities always get parentheses. And back to the range, negative infinity up to a positive 3. Because of the solid dot here, we're going to include that as a value. Here we have three different functions in one. We're asked what the domain is. So it starts at a negative 1 and it goes off into infinity because of this arrow right here. So negative 1 comma infinity includes negative 1. And now we're going to look at the y values. It starts here at 0 but does not include it because of the open dot right there. So I'm going to put a parenthesis, and it goes all the way up towards infinity because, again, this arrow here. Infinities, whether they're positive or negative, get parentheses. A step function is used for certain situations in which the graph has a constant value over sections of its domain. It's known as the greatest integer function, largest or greatest integer less than the given number. This is what it looks like right here. So f of x is equal to, two brackets, x, and then two brackets to the right. It looks like a staircase, and sometimes the steps are connected with vertical lines and sometimes they remain separate from each other. We're going to take a look at one that remains separate from each other. As you can see, we've got the steps going on right here, and they continue on infinitely. So the domain are positive, negative, infinity, and the range is the same as well. We want to find the following values. What is the value of y when the function has an x value at negative 1/3? So I'm going to go over to a negative 1/3, which is approximately in this area. I'm going to look up. I don't see any value, but I look down. I see the value is at negative 1. When the function has an x value at 2, what is the value of y? If I go to 2, I look up, I see two referenced values. One is an open dot at 1 and the other is a closed dot at 2. We're going to use the closed dot at 2 because that includes the value. However, the one with an open dot does not include the value. And then if we look at the function's value when x is 2.75, 2.75 is roughly in this area. So if we look up, the greatest integer function value is also at 2 because of this solid line. So it's included as the y value for when x are all values at 2 all the way up to close to 3, but not including 3. In the practice, we're asked to graph the following functions on the set of axes. We have to keep in mind the domains and only use those parts in the graph. So you can either do that on your graphing calculator and plot the points, or you can write it out. That's up to you. We're going to start at -3 and go down, or go up, all the way up to 1. You just got to remember you're going to use that as a reference point. That's going to be an open dot because there's no equal sign underneath the inequality at this 1 here. But you will use it as a reference point. So the absolute value of a -3 is a +3. That's the distance that -3 has away from 0. Distance is always positive, so it's always going to be a positive result, and that's the distance of 3. Absolute value of 2 is a +2. Absolute value of -1 is +1. Absolute value of 0 is 0. Absolute value of 1 is 1. So I'm going to plot the points -3, 3. -2, 2. -1, 1. 0, 0. 1, 1. Keep in mind that's an open dot. Be very careful because of no equal sign and the inequality for that value. And then you're going to draw your line. And this line makes sense. Use your straight edge. I don't have one on here. This graph makes sense because we know that absolute value has a V as its picture graph. Now for all values between and including 1 through 8, its function or y value is 4. So 1, 2, 3, 4, 2, 4, 5, 4, 6, 4, 7, 4, 8, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 4, 2, 4, 3, 4, 5, 4, 6, 4, 7, 4, 8, 4. And there's our line. And that's how you graph it. Okay, so a function is graphed on the set of axes below. So as you can see, there's 2. I see the brackets. Immediately I think of piecewise functions. And I can tell that I have a parabolic graph to the left here. And then I have a linear graph to the right here. So if we were to continue the linear graph to go down, where would it hit the x-axis? Well, it looks like it would hit at maybe, or where would it hit the y-axis? It appears as though it would hit the y-axis at about roughly at 1/2, if we would to guesstimate. So knowing what we know about slope and y-intercepts of lines, as you can see, it has an open dot at 1, so it's not including that value, and it's all values are greater than 1 if you go or read it all the way to the right side here. So immediately I look at all my selections here, and they all have domains that are greater than 1, and if we evaluate the first choice here, the y-intercept definitely isn't at a -2, so this isn't going to work. Okay, and here the y-intercept possibly could be at 1/2. If we look at choice 3, the y-intercept can't be at -7. And if we look at choice 4, 9/2 is approximately equal to 4.5. So it definitely isn't down at -4.5. So this is not going to work. So the obvious choice is choice 2. So which of the graphs represents these two functions? I have an absolute value up top, and I have a radical equation down at the bottom. So for all values of x that are less than 1, not including 1, but less than, has to be in the shape of a V. So these two are in the shape of a quadratic, so they are not going to work. So it's between choices 1 and 2. And the only one that it could be or should be is choice 2, because a radical operation has this kind of look, and this is a quadratic in choice 1. So it's choice 2. For number 4, the equation to determine the weekly earnings of an employee at the Hamburger Shack is given by W of x, where x is the number of hours worked. So in between the hours worked of 0 through 40, we're using 10 of x, and anything greater than 40, we're using the function down below. So we want to first determine the difference in salaries, so that's step 1, for an employee who works 52 hours. So I'm going to substitute that into the second equation, or the bottom one given in the piecewise function, versus one who works 38 hours. That's going to be the first equation. And then the second thing is to determine the number of hours an employee must work in order to earn $445. And then explain how we arrived at that answer. Okay, so we have 3 steps, or 3 things we need to do as a result of this problem. It's going to require a little bit more steps than that, however. So for the first one, an employee who works 52 hours is going to be substituted into the second equation, because the domain is given as x is greater than 40. So 15 times the difference of 52 minus 40 plus 400. And I get 15 times 12 plus 400, which is $580. And then for a person who works 38 hours, it's 10 times 38, which is $380. We're going to subtract the 380 from the 580, and we get a difference of 200. So the difference in salary is $200 for number 1. And for the second part, the number of hours an employee must work in order to earn $445. If we took the first equation, 10x, and set it equal to $445 and solved for x, as you can see, x is equal to 4450, and that doesn't fit the domain here, so we're going to have to not use that. So it makes more sense to set 15 times the quantity of x minus 40 plus 400 equal to 445 and solve for x in order to find the number of hours. So you're going to distribute as the first step 15 times x, and 15 times the negative 40 is 600, plus 400 equal to 445. 15x plus the sum of negative 600 and 400 is a negative 200, is equal to 445. Add the 200 to both sides, thus solving for x. In which we get 43. So 43 hours fits into the domain of the second given equation. And the explanation as to how we arrived at this answer is anything along the lines of what I just did and explained. So due to the fact that if we had solved using the first equation, it wasn't going to fit within the constraints of the domain. We used the second equation and we solved for x. So we set the second equation equal to 445 and solve for x. X to be equal to 43 hours, which fits the criteria of the domain. Number 5. At an office supply store, if a customer purchases fewer than 10 pencils and the cost of each pencil is $1.75. If a customer purchases 10 or more pencils, the cost of each pencil is $1.25. Let C be the function for which C of x is the cost of purchasing x pencils, where x is a whole number. So for all the values in between and including 0 through 9, we're going to graph the equation at $1.75x. So I would do that on your calculator and just copy the values. So the first value is at 0, 0. Second value is at 1 and 175. Third, 3 and 525. Oop, I forgot the second one. 2 is at 350. 3 is at 525. 4 is at 7. 5 is at 875. 6 is at 1050. Sorry that my points are a tiny bit off, but that's the best I can do given what I've got. 7 is at 1225. 8 is at 14. And 9 is at 1575. Okay, so they're all solid points. I'm going to do the best that I can and draw a nice line here. Okay, so for all values greater than and equal to 10, we need to graph for $1.25x. So obviously it's going to go on infinitely. We just have to include and start at 10. So 10, 1250. So as you can see, that's going to be less than buying 8 or 9 pencils with the other function. 11, 1375. 12 is 15. 13 is at 1625, which is 16 and a quarter, and so forth. So there's my second one, and it goes off to infinity. So the next part states that a customer brings 8 pencils to the cashier. The cashier suggests that the total cost of purchase of 10 pencils would be less expensive. State whether the cashier is correct or incorrect and justify your answer. So as you can see, this value here, for 10 pencils, it is indeed less than the value of purchasing 8 pencils. So the cashier is correct. Because based on the graph of the piecewise functions, the value of 8 pencils is greater than the value of 10 pencils. Okay, so Morgan can start wrestling at age 5 in Division 1. He remains in that division until his next odd birthday, when he is required to move up to the next division level. Which graph correctly represents this information? So as you can see, the differences between the open and closed dots, there's an open dot at 5, and he's definitely starting to wrestle at age 5, so he should be included at age 5, so this doesn't work. Okay, and then he moves up to the next division when he has an odd birthday, so he can't be in both Division 1 and Division 2, so this isn't going to work for choice 3. And this one excludes everything when he turns 5 or 7. Okay, so this one doesn't make sense. The one that makes more sense is for all the values including 5 through 7, he's wrestling in Division 1, and then he gets bumped up, that's the solid line here, at Division 2, or the solid line and dot at Division 2. So this is choice 1. Okay, so the table below lists the total cost for parking for a period of time on a street in Albany, New York. The total cost is for any length of time up to and including the hours parked. For example, parking for up to and including 1 hour would cost $1.25, and then parking for 3.5 hours would cost $5.75. Graph the step function that represents the cost for the number of hours parked. Okay, so from 1 to 2 hours, we're going to pay $1.25. So that's about this area right here. And then we're going to go all the way out to 2 with an open dot and a line. Okay, and that should be more halfway in between the 1 and the 1.5 for $1.25. It's just I'm in more of a congested area. Okay, so 2 starts at 250. That's going to be a closed dot. I'm going to draw a line all the way out to 3, where 3 would have an open dot. And then we're going to go to 3 to 4, closed dot. 4 is at 575. Nope. We're going to put an open dot at 4 and draw a line, and then go up to 575. Closed dot. Go over to 5, up to 575, open dot, draw a line. And then closed dot at 5 and 775. Go out to 6, open dot, line, and then at 610 we're going to have a dot. Okay, so there's our step function.